Have you ever wondered how the code we write in languages like C or Java is actually understood by computers? Because at the end of the day, computers only understand binary. So somehow, our human readable code has to be translated into something the machine can execute.
That's right, and that translation is done using something called as compiler. A compiler takes high-level code and converts it into machine instructions that the processor understands.
Exactly. And what's even more interesting is that inside this translation process, several ideas from theoretical computer science are actually being used.
One of those ideas is regular expressions, or often called as regex. Most of us first hear about them in compiler design courses, but the interesting thing is that regex shows up in many real-world systems outside of compilers as well.
That's exactly what we're going to talk about today. Regular expressions in real world. We look at what and where the idea came from and how something from automata theory ended up powering tools which we use every day.
Before we jump into the technical part, maybe we should quickly introduce ourselves.
Sure. Hello everyone. I am Dakshji and I am particularly interested in system programming and compiler construction. I always find it fascinating when theoretical ideas actually appear inside real software tools.
And my name is Samir Chahar. My interests are mostly around algorithms and how theoretical models eventually become practical engineering solutions. Regular expressions are a really good example of that connection between the theory and real world systems.
So maybe the best place is to start with the basic question. What exactly is a regular expression, Samir?
At its core, a regular expression is just a pattern used to match text. Instead of describing one specific string, a regex describes a set of possible strings that follow a certain rule.
So, for example, if we wanted to describe an identifier in a programming language, we could write a pattern that says an identifier starts with a letter and can be followed by letters or digits.
That is absolutely correct. In regex form, that might look something like lettered follows let zero or more letters or digits, which basically means start with a letter and then we can have any number of letters or digits after that.
And numbers can be described in a similar way. For instance, something like digit plus, which simply means one or more digits.
Patterns like these are extremely useful during the lexical analysis phase of a compiler, where the program gets broken into tokens. But something many people wonder is, were regular expressions originally created for compilers?
The question is interesting, but the answer would be no, because regular expressions actually come from theoretical computer science. They were introduced by Stephen Klein in 1951 while studying mathematical models of computation. So they started as a purely theoretical idea.
Pretty much, Clean describes something called as regular events, which could be built using three basic operations: union, concatenation, and repetition. Repetition being what we now call as the clean star, is that correct?
Exactly, Sami. For example, if we take symbols like A and B, we can construct expressions such as A pipe symbol B, which means either A or B, AB, which means A followed by B, and A star, which means zero or more repetitions of A.
And what's more really important is that the result proved by Clean was that regular expressions and finite automata describe the same class of languages.
Yes, you are right. This means any regular expression can be converted into a finite state machine, and that connection is exactly what makes regex useful inside compilers.
During the lexical analysis, the compiler reads the source code as a stream of characters, and its job is to group these characters into meaningful tokens, things like identifiers, numbers, operators, and keywords.
The patterns describing those tokens are written as regular expressions. Those expressions are then converted into finite automata that can actually run on a machine. Typically, the process goes from regular expressions to NFA and then the NFA being converted to DFA.
You are very correct. The first regex is converted into non-deterministic finite automaton, and then it is then using something called as the subset construction algorithm, the NFA is transformed into deterministic finite automaton.
And that deterministic finite automata essentially becomes the scanner, which recognizes tokens as the program is being read. But regex didn't become widely used in practice until an important algorithm was developed at the Bell Labs.
Are you talking about the Ken Thompson's algorithm? Is that right?
Exactly, you are right. In 1968, Thomson developed an efficient method for regex matching. Before that, pattern matching systems often relied on backtracking, which could be a slow process and the lengthy one. When expressions got complicated, Thomson's idea was different. Instead of exploring one path at a time, the algorithm simulates multiple NFA states simultaneously.
So, as the input string is read character by character, the algorithm keeps track of all possible states the automaton could be in. And because each character is processed only once, the algorithm runs in linear time, which makes it very efficient. This approach eventually became the foundation for classic Unix tools like grep.
I would like to add an interesting fact. The name grep actually comes from an old editor command which is g/re/p, which stands for Global Regular Expression Print.
That was a fun fact. So, overall, we got to know that today regular expressions appear in many practical systems. For example, when we use a website and it checks whether an email address or a phone number is valid, there's often a regex pattern behind that validation.
And also, in system administrators use regex extensively when analyzing log files. Data scientists rely on regex to extract patterns from large text datasets.
Yes, even a lot of development tools like IDEs use regex for advanced search and replacement operations. So even though regex is introduced in compiler courses, its application extends far beyond that context.
When you look at the bigger picture, it's pretty interesting how something that started as a theoretical idea ended up becoming such a practical tool. And many developers use regex almost every day without even realizing that the theory behind it comes directly from automata and formal language theory.
Whenever someone writes a regex pattern, they're essentially describing a language that a finite automaton can recognize, which brings us right back to the concepts we study in compiler design. So, from compilers to search tools, log analysis, and data processing, this same underlying idea keeps showing up. And that's what makes regular expression such a powerful bridge between theory and real world computing.
Thanks for listening, and we hope this discussion helped connect the concepts from compiler design with the tools which we encounter every day.
Thank you.